and welcome to the Chemistry Academy. In this video we're going to go over buffer solutions in relation to the Advanced Higher Chemistry course. So a buffer solution is essentially a solution that the pH of which will not change much, pretty much stays constant regardless of whether you add a small amount of an acid or an alkali. So from National 5 we should know that if we add an acid to an alkali it makes the pH move towards 7. And if we add an alkali to an acid, it will also make the pH move towards 7. However, with buffer solutions, the pH of the solution will not change when you add a little bit of an acid or an alkali. And this is because there are two substances within the buffer solution that basically remove any excess ions that could cause the pH of the water to change. So, got the definition of a buffer solution here. It's just something you probably want to learn word for word just in case you do get asked that question in your chemistry exam. So like I said, it's just a solution in which pH will remain pretty much constant if you add a small amount of an acid or an alkali to it, or a base. So you get two different types of buffer, and the difference between them is just really what types of substances make up the buffer solution. So you get an acidic buffer and a basic buffer. It's kind of gives away in the name. The acidic buffer is made with acid-based substances, whereas the basic buffer is made with basic-based substances. So for both of them, it's the same kind of substances that you need. You always need the weak acid or the weak base, and then a salt of that weak acid or a salt of that weak base. Now it needs to be an associated salt of whatever your acid and base is, and by that I mean, like if you've used ethanoic acid, it needs to be an ethanoate salt. If you use propanoic acid, it needs to be a propanoate salt. If you were to use benzoic acid, it would have to be a benzoate salt. The main weak base that you'll usually come across is ammonia, so normally it ends up being then an ammonium salt. But amines can also act as bases as well. That's the organic molecules that have NH groups on them, or NH2. So sometimes they can act as buffers as well. It's just something to bear in mind. They can act as bases, although the common base you will see is ammonia for the weak bases. So if you're asked a question to pick substances that would be suitable to make up a buffer, you're just looking for a weak acid or a weak base and a salt that's associated with that weak acid or a weak base. So like my examples here, you could have ethanoic acid and sodium ethanoate, or ammonia and ammonium nitrate. Okay, so just make sure the names kind of like match, if you like, and that would be your basic pair, your buffer pair, sorry. So if we then look at how the buffers actually work, and this is where it probably gets a bit more confusing, but I've tried to break it down here to make it as straightforward and logically possible to understand. So in each of the buffers you will have either a weak acid if it's the acidic buffer, and then a conjugate base ion, and they are the main substances that act as the buffer. In a basic buffer you would have a weak base and then a conjugate acid ion, and they are the main ions, or the molecules that are helping to maintain the pH and act as the buffer. In the acidic buffer, what happens if you add an alkali is it's the acid molecule that then helps out in that instance. So if you add more alkali, the weak acid will dissociate in order to produce hydronium ions, which will then remove the excess hydroxide ions. Okay, because the excess hydroxide ions that you've added by adding an alkali are being removed, the pH then doesn't end up changing, because as we know from National 5, pH increases as the concentration of hydroxide ions increases. So if we remove those hydroxide ions, the pH that we're adding in, the pH isn't actually going to change. Okay, so if you're adding an alkali, it's the weak acid molecule that acts as within the buffer mechanism, and it does that by dissociating to produce hydronium ions, which then go on to react with the hydroxide ions to remove them from the solution. If you add an acid, then it's the conjugate base ion that helps with the buffering mechanism. So that ion you'll get from your salt, and that's the ethanoate ion in this case. So the conjugate base ion will react with the excess hydroxide ions that you've put in by adding an acid, and then therefore removing them from solution. So because the hydronium ion concentration is not changing, the pH isn't going to change. Okay, so basically the way the buffers work is they keep the ratio of the hydronium ions to hydroxide ions constant, and they don't allow that to shift by the addition of adding those ions to the solution. So try to remember it's the opposite. So if you add an alkali, it's the weak acid that's going to act as the mechanism, buffering mechanism. If you're adding an acid, it's going to be the conjugate base ion that's going to act as the buffering mechanism. So the weak acid will produce more hydronium, dissociate to produce more hydronium ions, therefore removing the excess hydroxide ions you've added. The conjugate base ion will react with the hydronium ions that you've added into the solution to then therefore remove them from the solution, so the pH doesn't change. Okay, your head will eventually it will click eventually because it is kind of logical. And then if we look at the basic buffer, it's basically the same thing. If you add the acid, it's going to be the weak base molecule that helps out with the buffering mechanism. So ammonium is a bit different in terms of how it acts as a base. It accepts hydrogen ions or hydronium ions, so it will react with any excess hydronium ions that you add by adding in your acid to then therefore remove them from the solution, so the pH does not change. I realise I forgot to adding a base here, or adding an alkali. And then if you add in an alkali, it's your conjugate acid ion, which again you get from your salt, that will dissociate to produce more hydronium ions that will then remove the excess hydroxide ions from the solution, so your pH doesn't change. So hopefully the colour coding helps as well. As you can see, for both your weak acid and your conjugate acid, the reason for how they work in the buffer is the same. They both dissociate to produce the hydronium ions that will remove the excess hydroxide ions. And then in both situations, your weak base or your conjugate base ion, they will react with any excess hydronium ions in order to remove them from the solution. Okay. The last thing you really need to know about buffers is how to calculate the pH of them. This equation you will get at the front of the data booklet, and it's pH equals pKa minus log 10 times the concentration of the acid divided by the concentration of the salt. I put wee asterisks here just to remind you that you're best to put the concentrations both into moles per litre. Sometimes they're given to you in moles per litre, often they're not. However, you can have them both in moles, as long as they're both the same unit, but a lot of the time it's better just to keep it in moles per litre just in case. And if you do need to convert into moles per litre, obviously just remember that C concentration is number of moles over the volume. Okay, so yeah, that's it really in terms of the theory behind buffers. Hopefully that's helped you make a bit of sense of it all. It is a bit of a confusing topic for most people, but hopefully, like I said, the colour coding and laying out like this kind of helped you with getting it into your heads. So if you find this helpful, please give it a like, don't forget to subscribe, and I'll see you again soon.